Right. Yeah. Thank you. Hopefully you can see my screen all right.
Yeah.
Before I begin, I'll just mention real quick that in the Git repository under the Antares folder, if you want to get to this notebook, just follow this particular file. And if you want to work on Colab, you could follow this link over here. So for now, I'll share this notebook over here. So before we begin, some of the boilerplate material, you need to clone the Git repository. There is some data that we'll be working with, so cd into the right folder, install certain requirements. If you're working from the Colab notebook, these three steps should do that. If you're working by cloning the Git repository locally, then the appropriate cells will also do that for you. All right. So the typical scenario that we are considering over here, we are interested in multi-messenger astronomy. Over here, in particular, we are focused on multi-messenger astronomy with gravitational waves. So the typical scenario we're looking at is that a binary neutron star coalescence has been observed by the LIGO-Virgo-Kagra collaboration. And then starting in 03, the LVK broadcasts its discovery notices in the form of public alerts, which contain certain data products that help in follow-up of this trigger. And that's important because binary neutron stars could have an associated electromagnetic counterpart called the kilonova, which is a very exotic source, and we have seen only one of them. So just for completeness, I'll mention that the gravitational wave sky localization, which is one of the data products that is sent out by the LBK, it is basically a probability sky map. So the gravitational wave detectors cannot pinpoint the source in the sky. All they can give is this banana-shaped localization that depends on how many detectors have participated, and also certain other things like the signal-to-noise ratio, the bandwidth of the signal, and such. But the takeaway is that they can be of the order tens to thousands, sometimes even of the order 10,000 squared degrees, depending on how many detectors participated. And here is an example of GW170817, where the kilonova was spotted. But then the problem that we want to look at over here is that going ahead, there can be several contaminants in the field of view. So especially as we go ahead to more sensitive telescopes, the sky area is wide enough that it can have many other objects. So we need to select down to potential objects that we follow up. And this is important because we need to communicate these to downstream facilities. I know of one called Treasure Map. Apologies if I don't mention. I'm just more familiar with Treasure Map. So that scheduling further observation to find out the kilonova that can be facilitated. So for this tutorial, I'll be just considering simulated light curves. And that's because we don't really have data. We just have one kilonova that has been spotted. That was a very optimistic case. And also most of the data is proprietary, especially at the time of discovery. So at least from the region of the sky map, that is high probability. So we need to simulate mock alerts, mock objects to test scenarios like this, and that is what I'm using over here. So that's where really the notebook begins. I have, for this tutorial purpose, I have a few mock objects. So these are of the order, well, exactly 10 light curves that I have over here. 9 of them are contaminants, in a sense they are not kilonova, and one of them is a kilonova. So for those interested, we just got these by using a ZTF-like cadence and using the SNANA supernova analysis library to get these light curves. So let's look at a few. So this is what the kilonova looks like. And this is what one of the contaminants over here. I've plotted a salt to light curve. So you can see that the timescales are very different. The kilonova will evolve really fast, very few data points, and as opposed to a supernova, which will evolve over, say, of the order 2 month timescale. But then the crucial point is that all of these will have an associated sky map. By all of these meaning, of course, the kilonova is really truly associated with the gravitational wave event. So over here, we just associate a sky map. And say that in red over here, we have the position of the true kilonova, but you have all these contaminants that may be pretty close to the actual location of the kilonova, can have pretty high sky location probabilities, really. So that's the scenario that we are looking at when we would like to filter those out. So from the sky map, we would like to down select these blue points and hopefully, get one or two candidates that we follow up and hopefully also find the kilonova. So over here, I'm not going to demonstrate any of the Antares API because that has been demonstrated in other talks as well. Over here, what I'll mention of is like a simple filter that could potentially down select this. And the ideas will be very simple. You will look for a temporal coincidence with the gravitational wave, the trigger time. Check for consistency with the sky map, maybe associated with the galaxy catalog to find out where the nearest galaxy is. So for that, I have mocked up some trigger time. Of course, it has been curated such that it matches the trigger times of those objects that I showed above. We have the sky map that I plotted, and I'm also loading a catalog over here to, of course, in reality, it will be something else. And over here, the skein filter will do some simple cuts based on time. So if we have, for any of the object, we do have detections before the gravitational wave trigger time, we don't associate it with the kilonova, we reject it. We could take the location of the object and then use some helper tools provided by the LIGO SkyMap library to very easily get the, for example, the line of sight probability, certain measures, certain metrics, which could help us associate like the line of sight probability, the offset from that mode of that posterior that I showed, the 50 and 90% contour area. So if I go back to the sky map, these would have sky localization area. Maybe I take the 90%. And also the searched area, which is if I consider the sky map, if I take all of these pixels, rank them by their probability, and just count the number of pixels until which I reach my desired point, and multiply that with the area of each individual pixel, that gives me my searched area. So using all of these metrics, we can put, for example, a cut. Here, for example, I've said that the searched area, if it's more than the 90% area, I reject that particular object.
2 minutes left.
So, and finally, we could get some extra information out by matching with galaxy catalogs. So we could run this simple filter, and over here I'll just quickly go over the output. Most of them would possibly have detections before the gravitational wave trigger time, they'll be rejected. But for some of them, they would have a matching catalog, and we can down select out to the true kilonova, which will possibly be a part of this set. Now, here we have utilized only the temporal and the spatial information. We could also use the light curve, and this is very much of a work in progress. There is also already light curve classification code, which is a part of Antares, but it's difficult because we have very limited data. But we could enhance the classifiers with these contextual information like the sky map itself. So here is very preliminary results, which with very few data we have trained this on. See, if I take a look at this 1 BC as a function of time, we have the kilonova class probability. This is really a binary classifier, kilonova, not kilonova, going down very, very steeply. But then we also have, if I go down to the true kilonova, which has only 2 data points, we'll hopefully build a classifier that very quickly from the early data it can provide good classification probability. And this kind of tool, if it's incorporated in the broker, that will help us filter out Killenova with much more efficiency. So I think I'll stop there and I'll take questions.
Thank you. I don't see any question in the Slack channel. Okay, but if you have one, please put it in the Slack.